All right, and now let's have a look at the antiderivative for the trig functions for the entire family. I mean, not the entire family yet, because we have to start building up our skills here. But for now, we're turning our focus into some of the common trig functions. Okay, so you must have seen the following function. And back in your days that you were doing the differential calculus on these trig functions right here and taking derivatives. So now if we're looking at back in your days doing derivative of trig function, then everybody knows clearly that taking the derivative on this function sine of x will land us into cosine of x. And of course, anyone viewing this video shouldn't be surprised about this understanding. So the derivative of sine of x is going to be cosine of x. And all the explanation was delivered back in your days learning about differential calculus, taking derivative. But so now here we're doing antiderivative. And again, remind yourself, we want to know what function has. So think about, if now I'm asking what function has this cosine of x function as what function has cosine of x as its derivative? That's the famous question I keep asking myself right here. Or in other words, and now along with how I have already introduced that symbol over here, then this in one package is a symbol indicating to find an antiderivative. And so now we want to find, so in that way, we want to now find the antiderivative of cosine of x. Okay, so that relationship comes right here. This comes from our previous learning in differential calculus. And so now, in other words, I can say the antiderivative of cosine of x is going to be simply sine of x. But now this time, don't forget, plus c. All right, so now we all of a sudden, it's a rule that, it becomes a rule. It becomes a rule, admittedly. And then it comes straight forward from our previous understanding based on the derivative of sine of x has to be a cosine of x. So now taking the antiderivative of cosine of x is going to be sine of x, but additionally plus c right there. Okay, so again, constantly remind yourself what function has cosine of x as its derivative, and the answer was stated here. Okay, and so now along that way, let me bring up another one, and I can work on the other board right here of mine. So we also learned back in your days of study about studying about differential calculus, or taking derivatives on different functions. Then you also have learned that now if we took the derivative, if we're taking the derivative of cosine of x, of course in terms of x now for keeping it simple. So the derivative of cosine of x equals minus sine of x. So that was the derivative. Okay. So that was the derivative. So now allow me to approach the explanation in this way. Think about this. If the derivative of cosine of x is negative sine of x, then you can also extend this understanding of ours. And of course, at this point when you're learning about antiderivative, then you should be fluent with all of these, and as well as all of these properties in taking derivative. So it also makes perfect sense that you can say the negative cosine of x, when you take that derivative, or in other words, derivative of negative cosine of x should be, because in the way how we understand now fluently, the negative sign in front of a function just means we have a constant a constant coefficient being -1. Okay, so we can keep the negative sign there, but then the derivative of cosine of x based on this is going to be minus sine of x. So the derivative of cosine of x is negative sine of x, just by that. And then now I extend that. So just like what I said, we extend that understanding to explain further that. So in that way, consequently, that's what the arrow now is for. So consequently, the derivative of minus cosine of x must be minus here according to the coefficient rule for taking derivative. And then the derivative on cosine of x was known to be minus sine of x. And so now that gives me altogether the two minus signs here cancel out each other and making it a positive. So in other words, the derivative of minus cosine of x equals sine of x. Okay, so I mentioned this as a leading explanation that lead into the following result. So in that way, if we now in our the integral calculus that we're beginning our journey here with antiderivative, then thinking the reverse way, then now what function has sine of x as its derivative? What function has sine of x as its derivative? So now we're going to pretend that, hey, if this is already a derivative of some function, then we want to find the antiderivative, and that's what the symbol as one package is for. So what function has sine of x as its derivative? And the answer is right here. Okay, and so now with that we can formulate as following. The antiderivative of sine of x is cosine of x. And I mean minus cosine of x, as the answer is right here. Okay, and so now, but don't forget, plus c. All right, so we have this famous one right there to remember. So far we have learned, just now I put in your understanding, and it didn't even have to be a formal example. So now we just pull back understanding from previous learning about differential calculus back in those days when we were taking derivatives on different functions. Then taking derivative on different functions, then we were fluent with these understanding. And so now from that, now at our level, now in thinking about it in the reverse way, then now we produce these results right here. Antiderivative of cosine of x equals sine of x. And on the other hand, antiderivative of sine of x, okay, equals a negative cosine of x. And of course, any of these have to come with a plus c. Okay? And so, a few other things I have to mention. Now, trig family is not as simple as the power functions. And so, it will come and we will build our skills step by step, gradually. Okay? But, and this is what I mean right here. For example, right now, at our beginning level right now, in terms of learning how to find antiderivative, then at this very starting point, we don't know the answer to this yet. And then at some point later on throughout our time learning together, when we get to learn the kind of material that allows us to find this antiderivative, then we will have a definite answer later. So right now, this is an unknown answer. At our level right now, we have an unknown answer. And that's what I meant by, at this point, we did not know all answers to all antiderivatives of trig functions yet. Okay, we don't know the answer to all the antiderivatives of trig functions yet. And this is one of them. Okay, and as well as we have other functions, like say the secant of x. Taking the derivative of these functions is easy, but now going backward, we need to get some other special technique. So at our beginning level right now, this is another unknown one. Okay, this is another unknown one, and then there is another one along the trig families. There is the cosecant of x. Okay, and this is also right now at this moment unknown. And then we will later on in a quarter in our learning time together, we will later on learn the technique to find the actual antiderivative for these. Okay, and I also forgot to mention, so cotangent is another one if this was a trigonometry course, I taught I will teach my students that tangent, secant, cosecant, cotangent together with the sine and cosine that you have seen over there. Those are the 6 basic trig functions, because the entire family of all trig functions are built from all 6 of these. But unfortunately, at this point so far throughout our learning about antiderivative, we only know the antiderivative for sine of x and cosine of x previously. And so this one here is still unknown. Okay? This one here is still unknown. And so now I'm going to go ahead and clear my other board and introduce a few other one. I mean, it's not as special, but it's useful to know them. All right, so now back in our days before learning about differential calculus or taking derivative, learning about taking derivative on functions, then we've learned that taking the derivative of tangent of x. Now, I'm not trying to explain what the antiderivative of tangent of x is. Okay, I'm not trying to explain that. Okay, in the end, derivative for tangent of x still remains unknown for now, for the next few lectures right here, until we've learned the technique to get to that, and I will specifically bring up these problems again. Okay, but for now, I just want to recall the fact that when we take the derivative, okay, when we take the derivative of tangent of x, then that derivative gave us, okay, secant square of x. Okay, secant squared of x. So that means we can, out of nowhere, we can also come up with the following results. So if derivative of tangent of x equals secant squared of x, then, well, antiderivative of secant squared of x. I'm not forcing anyone to remember, but it's worth it to take note of this one. So the antiderivative of secant squared of x will simply be tangent of x plus c. Okay, so it's another one that's worth our attention a little bit, even though it might be a little bit unexpected that, you know, how come we don't know, how come we still haven't found, we haven't found the answer to the antiderivative of any of these basic trig functions yet. They all remain unknown for now. But all of a sudden, a really unexpected function like the secant squared, and all of a sudden we know the answer immediately. And that's simply because we know back in our days taking derivative of tangent of x, and I'm talking about taking the derivative back then of tangent of x was equal to secant squared. Okay, and so now if we are reversing that work right here, okay, if we're reversing that work, then antiderivative of secant squared, yes, will definitely give us tangent of x plus c right there. And so commonly enough, you can just now think about the routine here. You can go back and grab any of your famous derivative of a function that you've learned back in your days for taking derivative of function. And then you can always reverse that, and you can come up with yourself the antiderivative for some function. Maybe the function is not as commonly known. So think about back in our days taking derivative, then cotangent of x, derivative of cotangent of x is going to be minus cosecant squared of x, minus cosecant squared of x. Okay, and so in that way right here, in that way, just think about it. I can produce the following here, and it's similar to the argument I've made earlier for the cosine function. Then it means taking the derivative of cotangent of minus cotangent of x will be a positive cosecant squared of x. Okay, and so in that case right here, now I can formally get into another formula. We don't have to. No one is required to remember it, to memorize it, but it's worth to note that, and it's worth that to put that to put some attention on that. So cosecant squared of x, the antiderivative of cosecant squared of x, the reverse of that derivative work, the antiderivative, will be minus cotangent of x plus c. It's another formula that's worth to take note of. Okay, and so there are still a few more that like I said, it comes out. There are a few more that come out as a consequence of reversing those known derivative works that we have done back then. Okay, among the trig functions here, of course. All right. All right. So recall that I have introduced this brief table that summarized all of our previous learning in terms of finding antiderivatives for some of these common functions. So I started introducing the power functions. So primarily we had those power functions. Those functions in the power functions are in the form of an x to a power n right there. Okay. Then so in the work of taking antiderivative. Okay. So that's what I mentioned. So we came to the rule that the antiderivative for that, so that's what capital F is here, and once we land into capital F, we don't have to do this sign anymore, this antiderivative sign anymore. And later on, I will also, at the end of this lecture, I am going to give a formal name for that for this symbol as well, even though I will hold on to the real explanation of why it's given that name, the symbol's name, to the later lectures in the quarter, in the learning time together, in our learning time together. But so again, anytime we're looking at as a summary of what we've learned before we got into the trig function, then this table describes that taking the antiderivative of a power function, then we have a rule. And that rule is here simply we're going to produce x to the power n plus 1 and multiply that with a coefficient 1 over n plus 1. Okay? So this is the rule for us to calculate antiderivative on any power function. However, that rule has an exception, and the exception is, this rule will fail when our power is a negative 1. And so for that reason, I also showed earlier that so to break away from that exception, then specifically when it's power negative 1, when x is a power function but power negative 1, or another way of writing that, it's the 1 over x function, the famous 1 over x function. Then now recognizing this 1 over x function as the power, as the x to the negative 1, the same as the x to the negative 1 power, then the antiderivative is one special one on its own here. It is just natural log of absolute value of x plus c. So this is just the table, and of course I had to revise the table a little bit more to make it look more neat right here. And then we advance further after the exponential, after the power function, we advance further into the exponential functions, the function that involves the e to the x and all that, right? So in the most basic one, the antiderivative, if we attempt to take antiderivative, and again that's what the symbol here is for, taking the antiderivative on our function in the beginning, being if lowercase f of x being an e to the x, then the antiderivative, the capital F version, has to be e to the x, but additionally plus c. So any of these right here, and actually I missed a, so this also needs to be a plus c here, but then again the rule here is anywhere except, the rule worked, but anywhere except n equals negative 1. Okay, but then now, so back to what I was in the middle of saying, so generally anytime we're looking at e to the x, the antiderivative has to be e to the x plus c. And then I also extended that general e to the x antiderivative to a special version where it's e to the ax. There's a coefficient in front of the x in your exponential the arguments like that. Then the antiderivative is actually in the form of a 1 over a. That same a right here, 1 over a times e to the ax plus c. So this is everything you have seen prior to this point where I just now introduced the trig function. So in this way, how I revise my table a little bit, now we are ready to put our new functions in there. So aside from the power functions and aside from the exponential function, we just now learned that there are also the trig functions. Okay, so the trig functions. And let's put them here in the board and see. So, and let's summarize what we've done just earlier before I reintroduce, before I mention this table again. So we have learned just now that the antiderivative for sine of x, this is one of the famous trig functions. Okay, and so that antiderivative there is negative cosine of x plus c, and it will always work like that. Okay. And then right now allow me to introduce this as a special case, and then later on we will get a chance to nail this down right here. But generally speaking, anytime we're looking at sine, antiderivative of sine, but instead of x it's ax, like similar to the e to the ax right here, we can do sine of to the ax. The entire ax here is inside of your sine function, and it has a coefficient a in front of the x, inside of your sine function. And I did not formally introduce that earlier, but then here you can, the answer will be minus now 1 over a times cosine of ax plus c. So this is a special and a little more general case than that specific one. But so these are the two trig functions that we've just now learned, primarily based on the sine function. And then we also learned further that still among the trig functions, we had now antiderivative to a cosine of x function. Okay, and that will be sine of x plus c. Okay, antiderivative of cosine of x will be sine of x plus c. Okay, and then again in the special case, in any of these special cases, and I will prove. And how about I suggest this? Put a little star here so that you can remind yourself. So that to note that later on there will be a formal proof somewhere when we come to the right point, learning the enough technique to prove these, to prove this more generalized case right here. Okay, and then this similarly cosine of some general ax right here will be the antiderivative for that will be 1 over a times sine of ax, okay, plus c. Or now, as I suggest, you can also quickly verify my result here by taking the derivative here. Because now, as I keep saying, the antiderivative means we're looking for which function has this cosine of ax to be its derivative. And I just now told you the answer. So after watching this video, you can also independently verify on your own by simply taking the derivative on this right hand side column right here of the antiderivative. And once we land into this original beginning function right here, then that means this is the correct antiderivative. I mentioned this in the earlier part of the video, and I want to re-emphasize again. Anytime you want to verify whether somebody has handed you the correct antiderivative or not, you can just simply take the derivative of that answer, including the c right there, and as long as we still land into that original function before antiderivative, then that is the correct antiderivative. Okay, all right. So, and then in this trig function, now I'm going to have to swing back on my other board and continue adding into the trig function. All right, and so now continuing with the trig functions, we have also seen, okay, so let me continue with the trig functions. And then we have also seen earlier that secant squared of x, okay, that will land right into the antiderivative being tangent of x plus c. Okay, and then we also looked at the antiderivative where our starting function was a cosecant squared of x. Then that will give us the answer here is a minus cotangent of x plus c. Okay, but other than that, those other ones in the trig family functions, we still don't know the definite answer yet, and we have to wait. We have to wait until the day that we learn more techniques and be ready for finding those antiderivatives on our own. Yeah. Okay, so now aside from the trig functions, let me recall a few following. So we also had inverse trig functions. Many textbooks use the symbol arcsine. Okay, arcsine of x. Okay, that's a symbol for inverse trig function. I tend to write this as sine to the -1 of x right here. So it's just the notation that I'm more comfortable with. But many textbooks also use this symbol arcsine. These are both different ways of saying inverse trig function, inverse sine of x. Okay, inverse sine of x specifically. So taking the derivative on arcsine of x or taking the derivative on inverse sine of x right here, the answer is, okay, and they both come down to, so allow me to indicate with the two arrows like that, kind of like, so this is the notation that I'm more comfortable with. Some textbooks, I mean a lot of textbooks use this too, but I believe there are more textbooks going with this arcsine symbol right here. So it's for the students to know both. Okay, but anyway, so the answer to these, if we recall from your days taking derivative on inverse trig functions, then derivative of sine inverse is going to give us 1 over square root of 1 minus x squared. Okay, and so simply in that way, I am going to reverse the work right here. We found the derivative of this sine inverse function. In inverse sine function. Back then in our days of learning about derivatives. And so now that means reversing it, finding the antiderivative on this specific function. 1 over square root of 1 minus x squared. Finding the antiderivative of that function will simply be, now we can take that, treat that here in our beginning of the journey here as a formula. It gives me sine inverse of x, okay? Or you can alternatively call this arc sine of x. This is just an extra interpretation of that. So now it's another formula that's worth our attention. Okay? And then the same way, and then so the same thing here we also recall. So now you can see that I'm getting into the inverse trig functions. Then we also had cosine inverse of x. Okay, and many textbooks use the symbol arc cosine. So cosine inverse of x is the same as arc cosine, okay, of x. Arc cosine of x, or cosine inverse of x. So now taking the derivative on this function, they are the same. So it will land us into the following derivative. It's negative 1 over the square root of 1 minus x squared. Okay? And so in that way, now again, just like how I have been deriving other basic antiderivative rules like that, then now we recognize that anytime we're looking at the antiderivative of negative 1, so it's almost like the other one I just introduced, where the antiderivative land into the sine inverse. And here, negative 1 over square root of 1 minus x squared. Okay, taking the antiderivative of that will land us into this function right here, cosine inverse of x. Okay, and that is another formula that's deserves some attention of ours right there. So if we can remember it, even though I will never require any of my students to remember this, to memorize this, but it's worth to put it in your memory somewhere. And then, or you can call that this function here is alternatively regarded as a arc cosine of x. Okay. And then so now in addition to that, we also have seen back in the days that we were taking derivatives, then the derivative of tangent inverse of x. Okay, tangent inverse of x, or many textbooks also use the symbol arc tan here of x. Okay. So taking the derivative of arctangent will give us, so any of these two forms will give us the same derivative right here. That will be 1 over 1 plus x squared. Okay, 1 over 1 plus x squared. So in that way, now we are ready to reverse the work, and from the derivative, we're gonna take the antiderivative of this function, which will happen quite commonly with this kind of problem. So 1 over 1 plus x squared, the antiderivative for that, or taking the antiderivative on this work. So right now, this is again just an operation. It's to indicate that we have an action to be done on that function 1 over 1 plus x squared. So the antiderivative for that is going to be tangent inverse of x. Okay? Or alternatively, we can write that as, according to many textbooks, convention, arctan or arctangent of x. Okay? And that's how it is. And then again, there are a few more, but not as important as this one. So you can quickly grab any standard calculus textbook, okay, and review those for yourself and quickly summarize with these rules. And so now again, back on my board right here, back on the table, on the other board that I was continuously growing. Then so now we're about done enough with the trig function. And just now I showed the work on some of the inverse trig functions. So let's create another family for that. So in this table, so How about here we're looking at inverse. Okay, INV of mine stands for inverse. Okay, so inverse trig functions. Okay, so these are the inverse trig functions. So I'm looking at, let's say the first one here was, see, when we are doing this, 1 over, when we are taking the antiderivative on the positive 1 over square root of 1 minus x squared. Okay, when that action is done, when that operation is done on this special function 1 over square root of 1 minus x squared, how many times you're going to see this? It all depends on the kind of application you're doing out there. Okay, but now this for sure will give you the antiderivative being sine inverse. And now in this short table, allow me to use my own comfortable notation, sine with the superscript -1 right here, plus c. And that's our antiderivative, famously known for this function. Okay, and then we just now looked at another one. So there was so minus 1 over square root of 1 minus x squared dx. So that there gave us, okay, cosine inverse of x. And of course, don't forget the plus c. And then now the bottom part here is going to get a little tight in space right here, but I also mentioned that for the function 1 over 1 plus x squared, okay, and anytime we would like to find the antiderivative on that, okay, then that will land us into the antiderivative being known as tangent inverse of x, okay, and of course don't forget plus c. Okay, and so at this point with this table right here, this table did not show all antiderivatives out there yet, okay, but at least it summarizes enough, it has summarized enough basic antiderivatives for us, and mostly it rely on the algorithm, the understanding, the explanations that we're just simply reversing a known derivative, and then we're coming back with the antiderivative as listed here in this table. And the entire course waiting ahead for you is all about we learn different techniques to find an antiderivative on more complicated and more challenging the functions. Okay? All right, and so now as we have bit by bit developed our majority in taking antiderivative, then allow me to introduce another example where it could be a fun problem to pay attention to. Okay, and it's really every example here that we're doing worth every single bit of attention of ours right here. So in example 7 here, it's another IVP problem, initial value problem, that similar to the one I have introduced earlier in the earlier part of this video lesson right here, this video lecture. So I'm going to start out by having a given, so now I'm having some function h, but I only know h double prime, some given h double prime being a 12t squared plus a 24t minus 2. Okay, so that's the given information. And then from this given information we would like to, and then along with this information we are also given that h prime at 2 equals 74, and further we are given h of 2 equals negative 55. Okay, so with these three given information right here, we would like to find we want to find our actual function h of x, or h of t actually. Okay, find the final function h of t, and that's our goal right there. So in this way, after we have had some good experience, and as I said, we have already grown some majority in terms of the understanding of going from a derivative back to the function itself, meaning we're taking the antiderivative work essentially behind the scenes right there. Then see, what we're starting out here is an h double prime, and in our understanding from previous course in calculus, in differential calculus, then double prime means it's a second derivative. So what we are given here at start is a second derivative. So, but the problem wants us to find the actual function. So think about this a little bit right here. Back in our days, taking derivative, then to arrive at the second derivative, that means we have to take the derivative out of this function and take another derivative out of the first derivative. And so now think about the reverse way. If we started out having this double prime given, this second derivative given, then we must find the first derivative. We must find h prime of t first. Okay, so that we from there we will have access to find out h of t. And so the plan now is that first we have to be able to find out what h prime of t is, the first derivative of this function h of t, before we can find h of t. So, but finding h of t is the derivative. I mean, h double prime right here is the derivative of h of t. So now h of t itself in the reverse way is the antiderivative of this given double prime right here, or this given second derivative. So that means now I'm going to apply on top of this 12t squared plus 24t minus 2, I'm going to apply that operation to indicate that, hey, I want to find the antiderivative to this function. And see, so the notation here, the d here, for once in a while, I'm staying away from the x variable. So, and I will formally introduce this later. But see, the d expression here has to be consistent with the variables, the main variable of our function. So the main variable of our function here is a t. So I'm using a dt here. Okay, but in the end, that symbol and the dt right here and the d expression is one symbol, and indicating it's an operation. It's an operation that indicates to take the antiderivative of this function. All right, so with in what I said earlier, we have at this point gained some majority in finding antiderivative. So that can go a little quickly. 12t squared, once we take the antiderivative of that, it's going to become a 4t cubed, or maybe I shouldn't, okay, 4t cubed. Or maybe I shouldn't rush right here. So it's 12, that's the coefficient times, now the power rule on top of that is indicating for me it's a 1/3 t cubed. Okay, so earlier I was battling in my own, in myself whether I should rush the step a little bit, and I decided to still keep that a little bit more laid down right there. And so 24, I keep the coefficient 24 and the antiderivative for t, it's a power 1 right here, so it's going to be times 1/2 t squared. So every of the little steps right here came straight out from the power rule from our summary table earlier. And then this is a constant term connected with a minus sign, so it's going to be 2t according to the rule we have learned. And plus a big C. Okay, plus a big C. That's just for start right now. And so now we know that this is some incomplete or some general antiderivative h prime of t. This is antiderivative of that h double prime. Okay, but we gotta, in order to find the final h of t right here, we have to know what that c value is, and that's what this initial value is for. And so again, I call this problem, it's a problem that we find the final function, but in the end it's giving these initial conditions right here. And so in the end, the whole problem here, just like problem number 6, we had we call what we have here an initial value problem. Okay, so according to the given information, we know that h prime at 2 equals 74. That's given. It's an initial value that's given right here. So, but h prime of 2, according to what we have found in terms of the general antiderivative of h double prime, then this is and we can now go ahead and clean up the terms here a little bit in terms of simplifying the coefficients. And so I'm looking at so now I'm looking at 4 times t cubed, but t now is substituted by 2. So 4 times 2 cubed plus, and then 12 times t squared, but t now is substituted by 2. And so, and then minus 2 times t, okay, but t now is substituted by 2. And then plus c. And then, so all this here is, all that here is h prime at 2. Okay, and the initial condition is saying h prime at 2 equals 74. So that means I will equate all this here with 74. Okay, and so now let's do a quick calculation. All of that here before the constant c, it gives me 76 plus c equals 74. That comes straight out of our expression. And so now subtracting both sides by 76 right there, I'm looking at c equals negative 2. Okay, and so now our first derivative has been found now. So we started out with the second derivative, but now we found our first derivative. That is, okay, and so 4t cubed plus 12t squared minus 2t and minus 2. So that's our first derivative. Okay, but now having the first derivative is not our final ultimate the answer, because we need to go all the way to finding the actual h. And so now just one more step. So by 4, when we get to this point, right here, it is just like how we did work on on example number 6. But now this example is a little bit more advanced. It's going to add another step. So it's an IVP problem. It's an initial value problem, as the name I introduced earlier. But then in this case right here, we have to move on with 2 steps. And then be ready, as you become more advanced in math, you're going to have to deal with the kind of function where you have to take antiderivative multiple steps right here. Just like how back in the days we can take derivatives as many steps as we need to. And so in this way, now I'm ready for the next step, and allow me to erase this work of mine. And so now with our current h prime previously found being 4t cubed, okay, minus, or actually plus 12t squared minus 2t and minus 2 with our currently found h prime. Now I'm going to take the antiderivative of this h prime right here, and that's how I will land into my final h of t. Okay, and so going backward on any derivative, taking the antiderivative. That's the only key right there. All right, and so now the antiderivative, for now the general antiderivative for this is going to be, all right, so that now allow me to start picking up pace a little bit. So this is going to be 4t cubed together with canceling out, simplifying the coefficient. I'm looking at t to the 4th for the first term. Okay, now that becomes, so it's a plus, now it's become 4t cubed. Okay, and that becomes a minus t squared. Okay, and this last term here is a minus 2t. And don't forget, we need to add a different constant. So I don't want to use a c again, because c was for the previous step. So here, how about we can call it as a k? So k or c, or sometimes m or n, those are all just a constant that we added to our general antiderivative. So now this is the general antiderivative. Okay, that's indicating our general form of the h of t right here. It's a general solution. Okay, but now we need to look for a particular solution that match with the requirements. So the requirements here, I want the h of t function such that it satisfies h of 2 equals negative 55. And I should have also explained that. In our previous step right here. Once we have found our h prime of t to be 4t cubed plus 12t squared minus 2t plus c right here. See, it was a general solution, and we want to specifically look for that particular solution that satisfies this. Okay, that's another way. And then I believe I also explained that back in your example 6 as well. We want to find a particular solution to this. We want to find a particular value for c, so that our overall derivative here satisfies this given condition. And then from there we came up with our final particular h prime. And from this h prime now we are ready to move on to that h of t right here. And right now we're only currently at this step where we have already had the general h prime, general h of t, where we got hung up with that general plus. And I said earlier to add k, but no, I'm still writing a plus c here, so you can go plus k right there. Okay, because as I said earlier, I don't want to overuse a c. but it's a constant. So now I want to find the value for k to complete our h of t that satisfies this requirement, this condition right there. And so I also briefly mentioned that earlier. So now on my other board, I'm going to spend a minute to erase my board, and we're now ready for action. And so now we know that our h of t generally it is t to the fourth plus 4t cubed minus t squared plus, and actually another minus 2t and plus k. But in addition, it was given that h of 2 equals a negative 55. So that h of 2 now means anywhere I see the t variable in our current function h of t, I am going to substitute 2 in there. So h of 2 is going to give me 2 to the fourth power plus 4 times 2 cubed minus 2 all squared minus 2 times 2 plus k. And all of that there is needed to be negative 55 as the requirement was indicated. And so now we have 40 plus k equals negative 55. Okay, and so now in that way, now our k can be solved, our final constant here can be solved by subtracting the 40 from both sides. So we're looking at negative 95 right here. Okay, so so now this is our final answer. Our final h of t is concluded as following. h of t equals t to the fourth plus 4 plus 4t cubed minus t squared minus 2t and minus 95. Okay, and now we have come to the final particular solution for our h of t. Okay. All right, and so now in case you have heard from somewhere here and there prior to watching this video lesson, this particular video lecture right here, then you might have heard some terms about the integral and all that. So now I can start telling you informally. My word here is I can start telling you informally that the whole time we've been learning so far, I've been regarding to this as one symbol to indicate that it's an operation, it's an action, that we're taking action on a specific given function. So the whole symbol here in my explanation by far is one package. I mean, it's one package of symbols, okay? One symbol, really. That's I grouped together. I've been calling that. It's the symbol to indicate to indicate the operation that we were looking for, the antiderivative on this function, okay? But so now, what I'm about to tell you now informally is that at this point I will allow you, but I will come back and explain in depth the reason why it's being given such name, okay? And that's why I said earlier I'm telling you now informally, and then at some point later I will come back and explain the reason why it's given such a name. So now if you see this whole thing here, this whole problem here, including the f of x here, okay, this whole package now, so outside of the symbol here, so now the symbol together with the function, right, makes up an entire problem for us. And so this problem here now is famously regarded as, and as I said, I'm telling you now the name of this problem informally, and then at some point we will get to a formal explanation of why it's given this name right here. This problem here is regarded as the indefinite okay, taking the antiderivative of a function is the same as taking the indefinite integral. Okay, the indefinite integral of the function f of x. Okay, and so this whole problem right here, the answer that comes out is the indefinite integral. It's regarded as the indefinite integral of f of x. But then, just as I said, I'm only now telling you, I'm going to start telling you, it's just, of course, it's also more convenient that we can have, this name is a lot of times shorter and easier to say it out compared to using the term antiderivative and antiderivative. So here, just find the indefinite integral of f of x. And so now we informally learn this term. But then I will hold on to the explanation of why it's given such name until a few lectures later on, when I start formally explaining what a real integral is and a real definite integral is. Okay? And so now, from now on, anyone studying calculus with me is allowed to use the name indefinite integral in place of an antiderivative. So in other words, the indefinite integral, as a clarification, the indefinite integral is a different name of saying the antiderivative. It's a different way of saying it. Okay, and yes, we can take that informally for now, and then later on, as I said, we will get to that lecture where I will be able to explain the reason why we have given such name. Okay.